So essentially, like the main thing that LNN ILP adds on top of baseline LNNs is the ability to fill in different predicates from our data set, right? The way this works is that a user provides a template that approximates the general structure that we might expect to see. This template is defined as just a graph, vertices V and edges E. And the important thing is that it has this mapping function, which is basically going to map from vertices in the template graph to either logical operators or potential predicates that we can use at each node. So like Pavel mentioned, right, the gray boxes can be filled in with predicates from the data set, and then the orange ones are fixed operators that have different arguments they can choose from the children below them. And so what the authors do is they basically introduce math that makes it so that gradient descent will assign weights to these predicates and effectively fill in the template through backpropagation. So how exactly does this work? Well, the core idea is weighting. So we want to gate between different available predicates. And so the truth value when we're filling in from the database is actually just this weighted sum over available predicates. So to walk through step by step, we start with L, right? L is this mapping function from vertices in our template, and it gives us the available predicates at a particular node, okay? And so for each predicate, say X, Y, and Z, we want a weight that says whether this node should choose that predicate. And so it's just a simple weighted sum over the truth values of these predicates. Now, by default, right, a weighted sum is unbounded, right? These weights can take any real value. And we want this system to be interpretable. And one way to make it more interpretable is to make the weights sparse. So to make the weights sparse, right, the authors propose basically using ReLU to clip large weights. So the way this works is that basically the weighted sum on the last slide is right here in the parentheses, and we subtract it from the learned bias of the network. What this does is that when it's less than, when the weighted sum is larger than the bias, it's going to be negative, right? And so ReLU is going to clip negative values to 0, and so basically it's going to discard large weighted sums according to some learned bias. And so this is basically a way of making it so that the forward pass actually makes the weighted sum small and encourages small weights. It's similar to using like an L2 norm or something, except that it happens in the forward pass rather than as a projective. So what this does in the end is that like when you fill in your template, it says like, not just like a linear combination over X, Y, and Z, but only Y or only Z, right? So that's really important for interpretability. It means that even though the end result is a neural network, we can kind of read off like an actual logical structure from it. And so this formula is used almost verbatim to learn disjunctions. The only difference is that instead of doing weighting over the available predicates in the data set, we're doing weighting over the children at a particular disjunction node, right? So since it's a tree, right, there's children that are available, and we just have a weight for each one. And like before, right, that weight is sparse, so that ideally we have some kind of interpretability. The same formula, more or less, is used for conjunctions, except that a few terms are shifted around, so that mathematically it sort of represents a conjunction, like Matt was showing in the diagram. Again, they use the children and it's sparse. And then negation is just 1 minus x, except that we have to consider all of the possible assignments in the universe of assignments. So overall, that's how they make LNN more flexible, right? By being able to choose predicates at each node and so on, using just backpropagation. There's a few details, right? So like Matt mentioned, basically these LNN operators expect certain inequality constraints to be satisfied. And like we've seen in some other papers, right? People will solve this actually as like a constraint optimization problem. But instead, what the authors do is they kind of specify it in the forward pass. So basically, like they can use this thing called the double description method and a particular theorem that makes it so that a differentiable network layer basically enforces these constraints on weights and biases at a particular node. So, like, when we specify these inequality constraints, right, we just specify a matrix of coefficients and a vector of constants, right, so that AZ is less than B, where basically Z is the concatenation of weights and biases, like our parameters, right? They have to be constrained under, AZ is less than equal B. So they use this theorem down here, which is Minkowski-Weil, and it basically says that they can translate these constraints into rays and vertices describing a convex polyhedron. And the core thing is that they have to learn, they have to calculate mu and lambda to basically find weights and biases that satisfy the constraints. And so the way they do this is actually just with off-the-shelf network operators, right? So they use, max, softmax, and ReLU to actually just calculate mu and lambda. And then once mu and lambda are calculated, right, they can plug in epsilon and gamma from the double description algorithm, and then they can update their weights and biases so that they satisfy these constraints. In other words, right, you can use LNN without it blowing up, and so it actually represents like some logical operator. And the cool thing is that it's kind of more in the forward pass rather than like in the optimization procedure. But yeah, otherwise it's just a minor detail, and the core thing to take away is that like they define basically a version of LNN that can choose predicates flexibly from the data. And so now I think Pavel is going to talk about like how these pieces sort of fit together into an overall structure that can fit a new database.
Yeah, thank you, Lucas. So I want to take what Lucas presented and sort of take everything that we presented and put it all together so we have a clear image in here. So we started with a tree, right? So we had a tree with leaves taking predicates from the database. These are these guys. Then in the middle, in the core, we had these predicate type operators. And in this case, this is on conjunctions and disjunctions. And at the end, we had the final result that we want. So this is like putting it all together, and we talked about weights, right? So where are these weights? So the weights are learned in each of these cases, but besides the weights, we also, as Lucas mentioned, we have these constraints. So if we focus, let's say, on an junction, there's a bunch of things going on, right? So we have all this architecture basically ensures that these rays and vertices and lambdas and mu's are maintained and act as constraints that whatever we're learning the weights, everything does not implode and everything actually works. So that's sort of the higher level. But it doesn't just happen in the conjunction, it also happens in the disjunction. Exactly the same architecture, just different parameters. And then in the LNN pred, because it's not an operator, it's just weights. So this is like the big picture of all of it, right? So the more operators you have, the more of these types of things you would have. But as I said, like as a person, you have to come up with a template, and as a person, you have to ensure that the template is sound. Otherwise, it's not going to work. Sure what's happening. Okay, we're back online. Okay, so to conclude, so we wanted to summarize everything what happened. So, what are the limitations? What's the future work? If you're interested in this, what can you contribute further? So, as we mentioned, the templates, you have to pick them. You have to be smart about it. The first criticism is, let's say if you pick a very complex template, right, you're still learning the weights. So in theory, they could be like this artificial pruning by setting the weights closer to zero, but they, in practice, they will never be zero. So that's one improvement is like, can you prune a complex template? Another thing is, can you go further and actually let the model learn the template? So completely remove personality. And another criticism that we had was, at the end of it all, you're learning the LNN and then you're extracting the first order logic, but you still have this LNN that you learned. So we wanted to see, like the paper never mentioned, like what else can be done with it? Like what else can you take? So that's another direction to think about it. Like once you learn it, can you reuse it somewhere else? Can you adopt it somewhere else? So that's one thing that you could also explore.